So we're going to go over some sums of geometric sequences. So first let's just start with what is our equation. So our equation is the sum of the first n terms of a geometric sequence is S of n, so it's the sum of n terms, is a1, our first term, times 1 minus r to the n. So r was our ratio, n is how many terms, and on the bottom we have 1 minus r. Important again, when you put it in your calculator, you don't want to just put 1 minus r, you want to put parentheses around it so that you get the right answer. Okay, let's do a couple of examples. Let's start here. Let's find S of 10, so the sum of 10 terms of 8, 16, 32. What do I want to see? Well, first I have A1 is 8. I can see from 8 to 16, 16 to 32, my ratio is 2. So finding S10 says we're going to have our first term 8 times 1 minus 2 to the 10th power, and then divided by 1 minus 2. Again, I'm going to put that in parentheses. The bottom is really easy, so I think it would be better to do 1 minus 2 to the 10th and say I'm just going to divide by 1 minus 2, which is negative 1. I think that'll be the easiest way to do this and not have to put too much in your calculator. So 8 times 1 minus 2 to the 10th, and then dividing by negative 1, I get 8,184. Let's try it again. This one I made S of 20, so the sum of the first 20 terms, I have 1 over 25, 1 over 5, then 1, then 5. So I'm starting with a smaller number, 1 over 25, that's A1. Hopefully you can see the ratio is I was multiplying by 5, so R is 5. So to get the sum of the first 20 terms, I take the first term, 1 over 25, and I do 1 minus my ratio 5 to the 20th power, and then over 1 minus 5. So really important that you're seeing this number here, 20, is the same as the exponent here, which is 20. I'm going to make this 1 over 25. I'm going to keep 1 minus 5 to the 20th power. And again, on the bottom, 1 minus 5, that's negative 4. That'll be easier. So 1 divided by 25 times 1 minus 5 to the 20th power. And then I'm going to divide that by negative 4. This is a really big number. My calculator spit out something that says 9.536743164 e to the 11th. That is scientific notation. Maybe your calculator said times 10 to the 11th. What does that mean? It means there are 11 numbers after the 9. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go 10, 11. That's what the number would look like, really, really big. All right, let's see if we can get one a little smaller. This says let's find S of 15, given I have negative 3, positive 12, negative 48. My first term, negative 3, my ratio is negative 4, so important that you pick up there was a negative in the ratio. So the sum of the first 15 terms, there's my negative 3. 1 minus, now you have to put the negative 4 in parentheses when you tell it to the 15th power, and then I have 1 minus, I'm going to put negative 4 down there too in parentheses. I want to see that negative becomes a positive on the bottom. So I have negative 3, I have 1 minus negative 4 to the 15th, and then on the bottom 1 minus negative 4 becomes positive 5. So negative 3, 1 minus parentheses, negative 4 to the 15th power, and then I'm dividing by 5. This says my answer is negative 6, 4, 4, 2, 4, 5, 0, 9, 5. So really big answers here when we're looking at these geometric sequences. Right. This is the same thing, just said in a different way. So I have the sum from I equals 1 to 17 of 2 to the I. What does that mean? It means I have 2 to the 1, and then I have 2 squared, and I keep going up to 2 to the 17th. All right, so I'm looking for this sum. What do I want to know? I want to know, well, what was the first term? So the first term was 2. What was the ratio? The ratio was also 2. And how many terms do I have? I have 17. Okay. So my sum, S of 17, will be 2, my first term, 1 minus 2 to the 17th over 1 minus 2. Right, so just using the same formula. I think it's important to expand it out a little. I think it'll help you see what the first term is because sometimes that's a little hidden. So I have 2 times 1 minus 2 to the 17th power. So let's write again, here's what I'm doing. And on the bottom, I'm just going to divide by -1 so I don't have to put that whole divide by parentheses. I get 262,142, so 262,142. I want to do this for you again, make it a little bit bigger. So I have the sum I equals 1 to 14 of 8 times 3 to the I. I thought this was important to throw like a number in front. So let's think about putting the numbers in. So I have 8 times 3 to the 1 plus 8 times 3 squared, right? And I'm going to keep doing that until I get 8 times 3 to the 14th power, and I want the sum. The first term is 24. Okay. How is it increasing? It's increasing by 3, so that's my ratio. And how many terms do I have? I have 14. My sum, S of 14, is going to be equal to the first term, 24, 1 minus my ratio to the 14th power over, and then at the bottom, I have 1 minus R. Put that in parentheses. I have 24, 1 minus 3 to the 14th, and then on the bottom, 1 minus 3 is -2. Okay, so 24 times 1 minus 3 to the power 14, and then divide that by -2, and this gives me 57395,616. Again, really big numbers because we're doing something that's geometric. I can put the commas in if that kind of helps you to see that's 57,395,616. Okay, let's do a quick application. Let's say Sam works for a medical equipment company and his contract requires him to sell $500,000 worth of equipment his first year and increase his sales by 15% each year he is at the company. Assuming he meets his sales goal, find Sam's total sales for the first 8 years he works for the company. Okay. Really important that we're looking at a word problem, we need to pull out what's important from it. So the first thing I see is 500,000. That would be the first term. And then it's increasing by 15%. So whatever it was, it's going up by 15%. So this 1.15, this is R. So remember, you have to do that 1 plus with the rate. And we're looking for the first 8 years. So we're finding the sum for the 8 years. Okay, let's go over and give me a little bit more room to do that. So this S8 will be the first term, 500,000. And then I have 1 minus, I have 1.15. This was raised to the 8th power over 1 minus 1.15. And again, I'm going to throw parentheses there. You know what I'm going to do. I'm going to make this S8 equals 500,000. We're going to put this in the calculator. Order of operations is really important here, but I wanted to say on the bottom it's -0.15. So 500,000, 1 minus 1.15 to the power of 8, and then divided by -0.15. Okay, so here's what I got, 6863409, and I'm going to put 0.54. All right, so this is, here's the total, $6,863,409.54. Real quick, notice on the bottom, I did the 1 minus 1.15. I did not do that on the top. So order of operations says you do the powers and then the subtraction. So make sure you're doing that top and bottom, that you're really thinking about order of operations. Let your calculator do it for you, of course, but don't try to like shortcut anything. All right, one last little thing to talk about is the sum of an infinite sequence. So instead of saying we're going to stop the sequence somewhere, we're not. We're going to let go to infinity. Now, the only time we're going to be able to find the sum of the infinite sequence is when the value r, the absolute value of r, is less than 1. What does that mean? It means that r is between 0 and 1, or if it happened to be negative, then that same kind of thing, like we would have to switch it to be positive. So it could be little as long as it's like -1 to 0. That's why I put an absolute value, and I have a case of each of them for us to look at. So if that happens, if we have this r where the absolute value is less than 1, then the sum of the infinite sequence will be a over 1 minus r. So it comes out really nicely. So let's take a couple of examples and look at that. So I have the sum from I equals 1 to infinity of 4 times 1/2 to the I minus 1. What do I need to do? I need to keep that 4. I put it on top. I put 1 minus 1/2 on the bottom. I have 4. 1 minus 1/2 is 1/2. 4, I can keep 1 over 1/2 flips to 2 over 1, and I get 8. Let me write out a couple of the elements of the sequence just so you can see what we were doing. So we had 4, and then we had 1/2 to the 1 minus 1 is 0, and then I had 4, half, 2 minus 1 would be 1, and then I would have 4, 1/2, then it would be squared, right? So you keep seeing that this is going up. What's happening over time is this half is making it small. So the first term is 4, and the next one, 4 over 1/2 is 2, and then this is 4 over 4th, which is 1, then it's a 4th, and then it's 1 over 16. So it actually would be 1 over 8, and then 1 over 16. Let's make that an 8 now, and then 1 over 16. So it's getting smaller and smaller. So here's 4, 5, 6, 7. So 7 already, and then all this little stuff extra is where the 8 comes up, because this keeps getting smaller and smaller and smaller. Eventually it's headed toward a value of 0. So it's those first 3 terms that are really giving us the big part of this, and then the last little bit kind of adds up to 1. If that helps out in your understanding of what just happened. Let's try it again. I wanted to give you something that was negative, so I gave you -0.3. Same thing, I'm doing the sum. I equals 1 to infinity of 7 times -0.3 to the I minus 1. Really quick though for you, you do 7 over 1 minus, remember it's -0.3. This is 7 over 1.3. So I do 7 divided by 1.3. We're going to call this 5.38. Okay, so that one did get a little smaller. Why did it get smaller? Because this one would go negative, positive, negative, positive. So I have some negatives and some positives. Some of them cancel out, and the number got smaller in the long run, but it still has some weight to it. Okay, a little bit of an extension to this that I think is kind of cool to see is, what if we looked at repeating decimals? So let me give you an example of one maybe we're familiar with, is like 0.3. The line over it means it's repeating, right? So I have 0.3333. It's going on forever. I could break it into pieces and say the 0.3, it could be 0.3 plus 0.03 plus 0.003 plus 0.0003, right? It keeps going, but I just broke apart what does it mean to have a repeating 3. Well, what if I wrote that as a fraction? 0.3 is 3 over 10. 0.03 is 3 over 100. 0.003 is 3 over 1,000, right? It would keep going. And I could treat this as a geometric sequence because I have a first term, 3 over 10, and I have a ratio, 1 over 10, right? The denominator is the only thing that's changing, the numerator is staying the same. So it's just doing powers of 10 on the bottom. So I can take this first term with my ratio, and I can put it into this formula, a divided by 1 minus r that we just talked about. It looks like this. So now I have this sum, I equals 1 to infinity of 3 over 10 times 1 over 10 to the I minus 1. Okay, well, let's put that in the formula. So it says 3 over 10 on the top, 1 minus 1 over 10 on the bottom. So I just did my a over 1 minus r. 1 minus 1 over 10 is 9 over 10. How did I get that? 1 could be 10 over 10. I subtract 1, so 10 minus 1 is 9. And then we think, okay, well, what do we do with that? We say that 3 over 10 gets multiplied by 10 over 9. Remember, when we divide by a fraction, we multiply by the reciprocal. The 10s would cancel. So I have 3 over 9, which reduces down to 1/3. So we went from our 0.3 here becomes 1 over 3, which I think we know that. I think we know 1/3 is 0.333. What I think is cool to think about is that we started with 0.3 and we ended with 3 over 9. What's nice is any repeating decimal could be done this way. So if I had 0.44444, it's really 4 over 9, or 0.11111, that's 1 over 9. If you had two numbers repeating, so like 454545, then you would just divide by 99. So I would have 45 over 99. If you don't believe me, throw it to your calculator and you'll see. Nice to see how we go back and forth from fractions, because maybe we always taught you that, but maybe we didn't explain how it worked.